The photograph appeared on screens across the world on July 12, 2022. At first glance, it looked like countless astronomy images that had come before. A patch of sky filled with galaxies, spirals and ellipticals scattered across the darkness, points of light spanning the frame. Beautiful, certainly, but familiar. Astronomers had been photographing deep space for decades. The Hubble Space Telescope had already revealed tens of thousands of galaxies in similar deep field images. What could one more photograph tell us that we did not already know? Everything. This was not just another pretty picture. This was the James Webb Space Telescope's first deep field image, and it was about to shatter our understanding of cosmic history. The photograph showed a region of sky so small you could cover it with a grain of sand held at arm's length. Yet within that impossibly tiny field of view, Webb detected thousands of galaxies. Not thousands of stars. Thousands of entire galaxies, each containing hundreds of billions of stars. Galaxies so distant their light had been travelling toward us for more than 13 billion years. Galaxies that should not exist. Galaxies that were too massive, too bright, too structured, too mature for the age they appeared to have. Galaxies that violated everything we thought we understood about how the universe grew from the Big Bang. Within hours of the image's release, astronomers began analysing it in detail. They identified galaxy candidates at redshifts beyond anything Hubble had reliably detected. Redshift measures how much the universe expanded while light travelled from a galaxy to our telescopes. Higher redshift means greater distance and earlier cosmic time. Hubble's deepest observations had found galaxies at redshift 7 or 8, corresponding to when the universe was around 500 million years old. Webb's first deep field showed galaxy candidates at redshift 12, 15, even higher. The universe when it was just 200 to 300 million years old. Less than 3% of its current age. An epoch so early that standard cosmology predicted only the first small proto-galaxies should be forming. Tiny irregular clumps of stars slowly assembling into the grand structures we observe today. But the galaxies in Webb's image were not tiny and irregular. They were massive and structured. Some appeared to contain billions of stars already. Some showed clear morphologies with disks and bulges. These were not proto-galaxies caught in the act of formation. These looked like mature galaxies that had somehow already completed billions of years of evolution in a universe that was only a few 100 million years old. How was this possible? Where did these galaxies come from? How did they form stars so quickly? How did they assemble into organized structures in what should have been chaotic early times? The questions poured out faster than answers could be formulated. The image was just the beginning. Webb had barely started its mission. This was a test image, a demonstration of capabilities, taken during commissioning before science operations officially began. If this is what Webb could reveal in a test, what would years of dedicated observations uncover? The astronomy community erupted with excitement and confusion. Papers began appearing within days. Some questioned whether the high redshift galaxy candidates were real. Perhaps they were not as distant as they appeared. Perhaps photometric redshift estimates were wrong. Perhaps contamination or unusual spectral properties made nearby galaxies look like distant ones. Skepticism is healthy in science. Extraordinary claims require extraordinary evidence. And these were extraordinary claims. But as spectroscopic follow-up observations began confirming the distances, the skepticism faded into astonishment. These galaxies were real. They were genuinely at the extreme distances and early times that photometry suggested. Some of the most extreme candidates turned out to be closer than initial estimates. But many were confirmed at redshifts that should have shown only primordial darkness, with perhaps a few faint smudges of the first stars. Instead, Webb found fully formed galaxies shining brightly across billions of light years. The universe in its infancy was far more active, far more productive, far more galaxy-rich than anyone had predicted. This was not a minor adjustment to our timeline of cosmic history. This was not finding that galaxies formed 10% earlier than we thought, or grew 10% faster. This was discovering that major galaxy formation was already well underway when the universe was a small fraction of the age we believed was necessary. It was like opening a time capsule you buried last month and finding artifacts from ancient Rome inside. The dates did not match, the timeline did not work. Something fundamental about our understanding was wrong. Either our measurements were systematically flawed in ways we had not detected despite decades of refining techniques, or our theories of how galaxies form needed complete revision, or the universe itself was different from what our models described. Something had to give. Webb's revelation went beyond just finding early galaxies. The telescope also detected structures at intermediate distances that challenged expectations. Galaxies at redshift 2, 3, 4, corresponding to when the universe was 2 to 4 billion years old, showed properties that did not quite match simulations. They were more massive on average than predicted. They showed more active star formation. The discrepancies were not as dramatic as in the earliest galaxies, but they were present. A pattern emerged. At every epoch Webb observed, galaxies appeared more advanced than models predicted. It was not that one specific era was anomalous. The entire history of galaxy formation seemed to have proceeded faster and more efficiently than standard cosmology allowed. This forced a reckoning. For decades, the lambda CDM cosmological model had explained the universe beautifully. The cosmic microwave background, the expansion history, the growth of structure from tiny primordial fluctuations to the cosmic web of galaxies and clusters we observe today. Countless observations confirmed the model. It became the standard, the framework within which all cosmological research operated. But lambda CDM made specific predictions about when and how galaxies should form. Those predictions were being tested by Webb, and they were failing. Not completely, not in ways that invalidated everything lambda CDM explained successfully, but enough that the model could no longer be considered definitive. Something was missing, some piece of physics, some process, some aspect of cosmic evolution that we had not properly understood or included. The image that appeared on July 12th looked simple, a small patch of sky filled with galaxies, but it was the opening salvo in a revolution. Webb was not just a better telescope than Hubble. It was a different kind of telescope, probing wavelengths and distances that revealed an unfamiliar universe, a universe that had been there all along but hidden from view, a universe that was bigger, earlier, more complex than we imagined, and we were only seeing the beginning. Webb's mission had years to run. Thousands more observations, deeper looks, wider surveys, targeted studies of the most mysterious objects. Each observation would add to the picture. Each discovery would refine or challenge our theories. The universe Webb was revealing would not fit into the comfortable framework we had built. It was demanding that we expand our thinking, that we question assumptions, that we admit how much we still did not know. The image changed everything because it showed us that everything was not what we thought. The universe was far bigger, far stranger, far more full of surprises than we had dared imagine. And we were about to learn just how much bigger. Redshift 12.5. That number kept appearing in the early papers, analysing Webb's observations. Galaxies at redshift 12.5. According to standard cosmology, at that redshift, the universe was approximately 250 million years old, a quarter of a billion years since the Big Bang. This sounds like a long time by human standards, but cosmically, it is an instant. For comparison, Earth is 4.5 billion years old. Complex life took 3 billion years to emerge. Human civilization spans perhaps 10,000 years. Everything we consider ancient history occurred in the most recent eye blink of Earth's existence. Now imagine compressing all the processes that form a massive galaxy into just 250 million years after creation itself. That is what Webb was showing us. Galaxies do not form instantly. The lambda CDM model describes a hierarchical process. First, tiny fluctuations in the density of dark matter during the very early universe begin to collapse gravitationally. These small dark matter halos form, first, perhaps just millions of solar masses. Gas falls into these halos, cools, condenses, and forms the first stars. These stars live and die. Some explode as supernovae, enriching the surrounding gas with heavy elements and blowing gas out of the small halos. Meanwhile, the halos themselves are merging. Two small halos collide and combine into a larger halo. This merger process continues over hundreds of millions to billions of years. Gradually, through countless mergers, the small halos grow into larger ones. The galaxies within them grow correspondingly. Small irregular dwarf galaxies merge into larger irregular galaxies. Those merge into spiral or elliptical galaxies containing hundreds of billions of stars. This hierarchical build-up takes time, lots of time. Early simulations suggested the first substantial galaxies with masses comparable to our Milky Way should not form until the universe was several billion years old. Later simulations with improved physics pushed this earlier, suggesting massive galaxies could form by around 1 billion years after the Big Bang. But 250 million years? Impossible. There simply had not been enough time for enough mergers to occur, for enough gas to cool and form stars, for enough structure to assemble. The universe at that age should contain only small proto-galaxies, irregular clumps with masses perhaps 1% of the Milky Way. Actively forming stars, yes, but far from the mature, massive systems Webb was detecting. Yet there they were, galaxy candidates at redshift 12, 13, even 15. Initial mass estimates suggested some contained 10 billion solar masses of stars. 10 billion. That is approximately 10% of the Milky Way's stellar mass. For context, the Milky Way is a large spiral galaxy that has been growing for 13.8 billion years through continuous star formation and mergers with smaller galaxies. Finding galaxies a tenth that massive when the universe was just 2% of its current age was like finding a toddler the size of an adult. The proportions were wrong. The timeline did not work. Skeptics immediately questioned the mass estimates. Determining the stellar mass of a galaxy from its light is not straightforward. You must assume a stellar population. Young hot stars shine much brighter than old cool stars. A galaxy with the same mass could appear dramatically brighter or fainter, depending on whether its stars are young or old. The age of stars affects their colours and spectra. All of this must be modelled carefully. Perhaps the early mass estimates were wrong. Perhaps these galaxies appeared brighter than they should because they contained unusually massive stars, or were caught during a brief starburst phase when star formation was proceeding at extreme rates. If the masses were actually 10 times lower, around 1 billion solar masses, that would be much more consistent with expectations. Still surprising, but not impossible. Spectroscopic follow-up observations allowed better mass estimates. Spectroscopy measures the light from galaxies in detail across many wavelengths. This reveals chemical compositions, stellar populations, gas properties. It provides much more information than simple photometry, which measures brightness in a few broad wavelength bands. As spectroscopy confirmed the high redshifts and provided detailed spectra, the mass estimates held up. These galaxies really did contain billions of solar masses of stars. Some mass estimates decreased slightly as better data refined the analysis. But the galaxies remained shockingly massive for their age, orders of magnitude more massive than simulations predicted should exist at such early times. The morphologies added to the mystery. Some of these early galaxies were not irregular clumps. They showed disks, central bulges, structures that should take billions of years to develop. Disk galaxies form when gas settles into a rotating plane around the galactic center. This requires angular momentum to be distributed properly. Bulges form through mergers or dynamical instabilities. Both processes are well understood and both are slow. A galaxy needs to complete many orbital periods for disk structures to emerge and stabilize. At redshift 12, the universe was so young that galaxies should not have had time to complete enough orbits to develop mature structures. Yet there they were, disks and bulges visible in galaxies that should still be chaotic and irregular. How did this happen? Several possibilities emerged, none entirely satisfying. Perhaps star formation was much more efficient in the early universe than we thought. Maybe the first stars formed faster from primordial gas. Maybe they were more massive on average, producing more light per unit mass. Maybe feedback from supernovae and stellar winds was less effective at suppressing star formation than in the present-day universe. If star formation proceeded 10 times faster than our models assumed, galaxies could accumulate mass 10 times faster. But this requires pushing star formation efficiency to extremes that seem physically implausible. There are limits to how fast gas can cool and condense into stars. Even if every available gas cloud formed stars as efficiently as possible, could it happen fast enough to build 10 billion solar mass galaxies in 250 million years? The calculations were difficult, but suggested no. Perhaps the initial conditions were different than we assumed. Standard inflation models predict tiny quantum fluctuations that get stretched to cosmic scales and become the seeds for structure formation. These fluctuations have a specific statistical distribution. What if reality differed slightly from the simplest inflation predictions? What if fluctuations were slightly stronger on certain scales? This could allow dark matter halos to form earlier and grow faster. If halos formed even 50 million years earlier than standard predictions, that would give galaxies more time to assemble. Combined with somewhat more efficient star formation, maybe the early massive galaxies become plausible. But this requires fine-tuning the fluctuations to get the desired outcome. Why would nature choose initial conditions specifically arranged to produce early massive galaxies? Modified dark matter physics offered another approach. If dark matter is not cold, meaning the particles move slowly in the early universe, but instead has properties that allow slightly faster structure formation, this might help. Or if dark matter interacts with itself or with normal matter in ways we have not detected, these interactions might affect structure formation rates. Dozens of alternative dark matter models exist. Some predict earlier structure formation than cold dark matter, but they also make other predictions about structure at later times or on different scales. Most fail some observational test when confronted with the full range of cosmological data. Finding a dark matter model that explains early massive galaxies without breaking everything else, Lambda CDM explains, successfully proved very difficult. Perhaps the issue was more fundamental. Perhaps the hierarchical model of galaxy formation was incomplete. Maybe galaxies do not only form through slow bottom-up merging, perhaps some galaxies can form more directly. In the very early universe, when the gas was primordial and had not yet been enriched with heavy elements from earlier stars, perhaps large gas clouds could collapse directly into massive galaxies. This top-down formation would bypass the slow merger process. A large dark matter halo could accrete enormous amounts of gas in a relatively short time. That gas, uncontaminated by previous star formation, might cool and form stars extremely efficiently. Within a few 100 million years, you could build a massive galaxy. This scenario had problems too. Why would top-down formation occur in the early universe but not later? What stops it from being the dominant mode of galaxy formation at all times? If it works so well early, why do we not see evidence for it at lower redshifts? The switch from one formation mode to another requires explanation. Perhaps the enrichment of gas with heavy elements changes how it cools and forms stars, suppressing top-down formation after the first billion years. Perhaps the intensity of radiation from the first stars and quasars heats gas and prevents large-scale direct collapse after a certain epoch. These are speculations requiring detailed modelling to test, but they point toward the kind of new physics that might be needed to explain what Webb was seeing. What became clear as more data accumulated was that the problem was not going away. Initial hopes that the highest redshift galaxy candidates would turn out to be false positives were disappointed. Most were confirmed. The universe really was producing massive galaxies when it was just a few percent of its current age. This was not a few anomalous objects that could be explained as rare lucky circumstances. This was a population. Numerous massive galaxies at these early epochs. The statistics might be uncertain. We cannot yet determine exactly how common such galaxies are, but they are there in sufficient numbers that they represent genuine cosmic evolution that lambda CDM struggles to explain. The galaxies that should not exist do exist, and their existence is forcing cosmologists to reconsider fundamental assumptions about how the universe grew from the Big Bang to the cosmic structures we observe today. Stand in a dark field at night, far from city lights. Look up at the sky. The darkness between stars seems complete, empty, devoid of light, but it is not. If your eyes were sensitive to infrared wavelengths, that darkness would glow, not uniformly, not brightly, but softly, with the accumulated light from countless distant galaxies. This is the cosmic infrared background, the combined emission from all the galaxies in the universe, summed together. Astronomers can measure this background. It tells them how much light the universe has produced across cosmic history, how many stars have shone, how much star formation has occurred. Before Webb launched, astronomers had measured the cosmic infrared background using previous infrared telescopes like Spitzer. They knew approximately how much light should be there based on counting galaxies at different distances and adding up their emissions. The numbers made sense. The measured background matched the expected contribution from observed galaxies reasonably well. There were uncertainties, especially contributions from very distant galaxies that were too faint for Spitzer to detect individually. But overall, the cosmic infrared background seemed consistent with lambda CDM predictions about cosmic star formation history. Webb changed this. As Webb began detecting galaxies at higher redshifts and in greater numbers than previous telescopes, a discrepancy emerged. There appeared to be more light in the cosmic infrared background than the population of known galaxies could account for. Not dramatically more, not factors of 10, but significantly more than uncertainties could explain. Where was this excess light coming from? The obvious answer was from galaxies we had not yet detected individually. If many faint distant galaxies existed below Webb's detection threshold, their combined light could contribute to the background, even though we could not see them one by one. But this explanation had problems. Extrapolating from detected galaxies to predict how many fainter ones should exist relies on understanding the galaxy luminosity function. This describes how common galaxies of different brightnesses are. Brighter galaxies are rarer, fainter galaxies are more numerous. The relationship follows a specific mathematical form that has been measured at various cosmic epochs. If you know the luminosity function, you can predict how many galaxies too faint to detect individually should contribute to the background. When astronomers did this calculation using Webb's measurements of the luminosity function at high redshifts, the predicted background contribution fell short of measurements. Even accounting for all the faint galaxies that should exist, there was still excess light. This suggested the galaxy population was different than we thought. Perhaps there are more faint galaxies than the luminosity function predicts. Perhaps the luminosity function changes at high redshift in ways we had not anticipated. Perhaps star formation was more widespread in the early universe than models suggested. Each possibility pointed toward the universe being more active and productive in its youth than lambda CDM described. More stars forming, more galaxies assembling, more light being produced. The universe was simply brighter than we predicted. Another possibility was that the early galaxies were intrinsically brighter than expected. Maybe early stars were more massive on average than stars forming today. Massive stars shine much more brightly than lower mass stars. If the initial mass function, describing the distribution of stellar masses, was skewed toward higher masses in the early universe, each galaxy would produce more light for a given amount of stellar mass. This would make the universe appear brighter without requiring more galaxies or more star formation than predicted. Just different kinds of stars. There are physical reasons why early stars might be more massive. The first stars formed from primordial gas containing only hydrogen and helium. No heavy elements existed to help the gas cool efficiently during collapse. Without efficient cooling, gas clouds cannot fragment into many small pieces. They form fewer, more massive stars. These first stars, called population 3 stars, might have been tens to hundreds of times more massive than typical stars today. They would have been extraordinarily bright, but very short-lived, exploding as supernovae within just a few million years. After enriching the surrounding gas with heavy elements, subsequent generations of stars would form with more normal mass distributions. If Webb was detecting galaxies during the era when population 3 stars dominated, that could explain the excess brightness. But population 3 stars should exist only during the very first stages of galaxy formation, before significant enrichment. Most of the early galaxies Webb detected should already be past this phase. They should already contain metals from earlier supernovae. Their spectra show evidence of metals in many cases. So population 3 stars might contribute, but probably cannot fully explain the brightness excess. Perhaps the excess light came from sources other than stars. Supermassive black holes at the centers of galaxies accrete matter and shine brilliantly as quasars or active galactic nuclei. These can be extremely luminous, sometimes outshining their entire host galaxies. If supermassive black holes formed earlier and were more active in the early universe than predicted, their contribution to the cosmic infrared background could be significant. Webb has indeed found evidence for surprisingly massive black holes at high redshifts, growing faster than expected. Perhaps black hole accretion was a major component of early cosmic light production alongside stars. Another exotic possibility was that the excess light came from dark matter. Some speculative dark matter candidates can decay or annihilate, producing photons. If dark matter was more active in the early universe, perhaps due to higher densities, before expansion diluted it, the photons from dark matter physics might contribute to the cosmic infrared background. This seems far-fetched. Dark matter is supposed to interact very weakly with normal matter and light, but we do not actually know what dark matter is. If it has unexpected properties, it could potentially produce detectable light under extreme early universe conditions. What was clear was that the universe, in its first billion years, was more luminous than expected. More light was being produced from more sources or more efficiently than lambda CDM predicted. This tied directly to the problem of early massive galaxies. If galaxies formed faster and grew larger earlier, of course the universe would be brighter. The two observations reinforced each other. The cosmic infrared background measurement was independent of galaxy surveys. It did not rely on detecting individual objects, yet it pointed toward the same conclusion. Something about the early universe was more active, more energetic, more productive than our models described. This mattered for understanding cosmic history. The total amount of star formation over time is constrained by observations of element abundances, the cosmic infrared background, galaxy properties today, and other measurements. These all have to be consistent. If the early universe was significantly brighter than predicted, that means more star formation occurred early. But the total star formation across all time is constrained. If more happened early, does that mean less happened later? Or does it mean the total is larger than we thought? Each possibility has implications for other observations. The web of constraints from different measurements has to fit together self-consistently. Webb's finding of a brighter early universe was pulling on that web, creating tensions that rippled through multiple areas of cosmology. The brightness excess also related to cosmic reionization. The first stars and galaxies emitted ultraviolet radiation that ionized the neutral hydrogen pervading space. This reionization process transformed the universe from neutral to ionized, allowing light to travel freely. The timing and sources of reionization are important cosmological questions. If more galaxies existed early, or if they were brighter, reionization could have occurred earlier or faster than predicted. Measurements of the cosmic microwave background constrain when reionization happened. If galaxies were bright enough to reionize the universe earlier than those constraints allow, something is inconsistent. Either the galaxy population estimates are wrong, or the reionization models are incomplete, or the cosmic microwave background interpretation needs revision. Every measurement connects to others. That is what makes cosmology powerful, but also fragile. When one piece does not fit, the entire framework strains. Webb's observations of a brighter early universe did not fit cleanly into lambda CDM. Something had to adjust. Either our models of star formation and galaxy evolution needed significant revision to allow the brightness Webb observed, or measurements of the cosmic infrared background had systematic errors that created spurious excess light. Or perhaps lambda CDM itself was incomplete in ways that affected early universe physics. The community was working through these possibilities, but the pattern was clear. Everywhere Webb looked, it found more than expected. More galaxies, more massive galaxies, brighter galaxies, a more active early universe. The cosmos was bigger, brighter, more full of life in its youth than we had imagined when we built our models from observations limited to what earlier telescopes could see. Webb was showing us what we had been missing, and it was a lot. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies held together by mutual gravitational attraction and embedded in enormous halos of dark matter. The clusters themselves organize into even larger structures called superclusters, chains and walls of galaxy clusters spanning hundreds of millions of light years. Forming these structures takes time. Dark matter collapses first into small halos. Those halos merge into larger halos. Galaxies form in the halos. Eventually, the halos grow large enough and dense enough to become galaxy groups. Groups merge into clusters. Clusters link along filaments into superclusters. Lambda CDM describes this hierarchical process in detail. It makes specific predictions about when structures of different sizes should appear. The largest structures form last because they require the most mergers and the most time to assemble. Webb found massive galaxy protoclusters at redshift 7. Redshift 7 corresponds to when the universe was roughly 750 million years old, about 5% of its current age. Protoclusters are regions where many galaxies are gathered in a small volume, destined to eventually merge into a massive cluster, but not yet gravitationally bound into a single system. Finding protoclusters this early was not impossible. Lambda CDM allows for some structures to form in the densest regions where initial fluctuations were strongest. But the protoclusters Webb observed were more massive and more concentrated than predictions suggested should exist at that epoch. One protocluster contained over a dozen massive galaxies within a region just a few million light years across. Each galaxy appeared to be forming stars vigorously. The combined star formation rate exceeded thousands of solar masses per year. The total mass of the system, including dark matter, was estimated at trillions of solar masses. This was a structure that looked like it should be a few billion years old, based on how massive and developed it was. Yet it existed when the universe itself was less than a billion years old. How did so many massive galaxies gather together so quickly? How did the dark matter halo grow to such enormous mass in such a short time? The issue was not just that the structure existed, but that it seemed so advanced. Protoclusters are supposed to be in early stages of assembly. Galaxies should be widely separated, just beginning to fall toward their common center. The merging process that turns a protocluster into a bound cluster takes hundreds of millions to billions of years. But Webb's high redshift protoclusters showed signs of being more evolved than this picture suggested. The galaxies were close together. Their velocities indicated they were already interacting gravitationally. Some showed signs of tidal distortions from close encounters with neighbors. This looked like a system well along in the collapse process, not one just beginning. Similar issues appeared with smaller structures. Galaxy groups, containing a few massive galaxies, should form earlier than clusters. But even groups found at very high redshifts appeared more advanced than expected. The member galaxies were too massive. The groups were too compact. The dark matter halos were too dense. Everywhere Webb looked at early times, structure appeared more developed than lambda CDM predicted for those epochs. It was not just galaxy masses that were problematic. It was the entire hierarchical structure formation process that seemed accelerated. Why would structure form faster? Gravity is gravity. It operates according to well-understood physics. Making structure formation happen faster requires changing something fundamental. Either the density of matter was higher, allowing stronger gravitational collapse, or dark matter was distributed differently than assumed, with more extreme peaks and valleys that collapse more readily. Or gravity itself was stronger in the early universe, perhaps through modifications to general relativity that only manifest under certain conditions. Each possibility had been explored in attempts to explain other cosmological puzzles. Now they were being revisited in light of Webb's observations. Perhaps the initial conditions from inflation were different. Standard inflation models predict Gaussian random fluctuations with a specific power spectrum describing fluctuation strength at different scales. What if reality differed? What if fluctuations were stronger on certain scales? What if the distribution was not quite Gaussian, showing more extreme peaks? Non-Gaussian initial conditions could produce more early structure without changing the physics of gravitational collapse, but they would require modifying or extending inflation theory in ways that are not obviously necessary to explain other observations. We would be complicating the early universe specifically to explain what Webb saw, rather than being forced to by other independent evidence. Dark matter properties offered another avenue. If dark matter could collapse more efficiently than cold dark matter, forming denser halos earlier, this would accelerate structure formation. Self-interacting dark matter might do this. If dark matter particles scatter off each other, they can dissipate energy and sink deeper into gravitational potential wells, creating denser concentrations. Or if dark matter has complex internal structure, perhaps existing in multiple states or species, this might affect collapse rates in ways simple cold dark matter does not capture. Modified gravity theories could also potentially explain accelerated structure formation. If gravity is stronger on certain scales or at certain epochs, structure grows faster. Some modified gravity theories are specifically designed to avoid dark energy by making gravity weaker on very large scales, which causes acceleration without dark energy. But these theories can also affect structure growth. Careful modeling is required to see whether any modified gravity theory can simultaneously explain cosmic acceleration, match cosmic microwave background observations, and allow the early rapid structure formation Webb observed. Most attempts fail at least one of these tests, but perhaps some version exists that works. The structures Webb found were not just slightly more advanced than predicted, They were dramatically so, factors of 2 to 5 more massive, or more concentrated, or more evolved than simulations produced at comparable epochs. This was not subtle. This was not something that minor tweaks to models could fix. This required either seriously revisiting how structure forms or accepting that our understanding of the early universe is missing major pieces. The latter seemed increasingly likely as more observations accumulated. The universe Webb was revealing was simply different from the one Lambda CDM described. Not completely different. The overall framework still captured cosmic expansion, the Big Bang origin, the growth of structure from small fluctuations. But the details were wrong in systematic ways that suggested fundamental incompleteness rather than minor errors. Perhaps most troubling was that the discrepancies appeared at multiple scales and multiple epochs. It was not just one specific structure or one specific time that looked wrong. Everything in the early universe seemed accelerated. Galaxies too massive, clusters too advanced, star formation too vigorous, Ryanization too early, the cosmic infrared background too bright. Each problem might individually be explained by special circumstances or measurement uncertainties. Together they created an overwhelming pattern. The universe had structure before it should. It was more organized, more mature, more evolved at every epoch Webb observed than Lambda CDM allowed. Something was fundamentally wrong with the timeline. Either the universe was older than we thought, giving more time for structure to form, which contradicted cosmic microwave background measurements, or structure formed faster, which contradicted our understanding of gravitational collapse physics, or both were somehow true, requiring revisions to multiple areas of cosmology. Webb was not just finding individual anomalies. It was revealing systematic failures of our best model across the board. The structures that should not exist were everywhere, and they were forcing cosmologists to confront the possibility that the universe is simply bigger, more productive, more complex than the models we built from limited earlier observations ever captured. Supermassive black holes lurk at the centers of most large galaxies. Our Milky Way harbors one containing about 4 million solar masses. The galaxy M87 hosts a monster exceeding 6 billion solar masses. These are not unusual. Survey after survey finds that nearly every substantial galaxy contains a central supermassive black hole. The masses correlate with galaxy properties. Larger galaxies have more massive black holes. The relationship is so tight that it suggests black holes and galaxies co-evolve, growing together over cosmic time through some interconnected process we do not fully understand, but know is important. Supermassive black holes also power quasars, the most luminous persistent objects in the universe. When matter falls toward a black hole, gravitational energy converts to heat and radiation. Accretion disks surrounding black holes shine brilliantly, sometimes outshining their entire host galaxies by factors of hundreds or thousands. Quasars can be detected across the observable universe. They serve as beacons marking the locations of supermassive black holes actively feeding on gas and stars. By studying quasars at different distances, astronomers trace the evolution of supermassive black holes across cosmic history. They see how black hole masses change over time, how common they are at different epochs, how their activity levels evolve. Before Webb, the most distant quasars known existed at redshift, around 7.5, corresponding to roughly 700 million years after the Big Bang. These were already surprisingly massive, black holes containing hundreds of millions to billions of solar masses. This was puzzling because black holes grow through accretion of matter and through mergers with other black holes. Both processes take time. A black hole starting from a stellar mass seed, perhaps 10 to 100 solar masses formed when a massive star collapses, would need to accrete matter constantly for hundreds of millions of years to reach a billion solar masses. even under optimal conditions, with unlimited gas supply and accretion at the theoretical maximum rate, called the Eddington limit, growing from stellar mass to billion solar mass in 700 million years, is difficult. It requires nearly continuous feeding at maximum rate. If the black hole stops accreting for any period, if its gas supply gets depleted, if feedback from the accretion process blows gas away, growth slows and the timeline extends. Webb found quasars at higher redshifts, redshift 10, redshift 11, even candidates at redshift 13, though spectroscopic confirmation for the most extreme candidates was still pending. These quasars hosted black holes with masses exceeding 1 billion solar masses when the universe was just 300 to 500 million years old. How did black holes grow so massive so quickly? The timeline seemed impossible, even starting from the most massive possible stellar remnants, even accreting at absolute maximum rates without interruption. Reaching these masses in the available time stretched the physics to breaking point. Perhaps the seeds were not stellar mass. Perhaps supermassive black holes did not grow from individual star collapses, but formed through direct collapse of enormous gas clouds in the early universe. Under special conditions, a gas cloud containing tens of thousands to millions of solar masses might collapse directly into a black hole without fragmenting into stars first. This would create a much larger seed, perhaps 10,000 to 100,000 solar masses. Growing from this larger seed to a billion solar masses is easier, but direct collapse requires very specific conditions. The gas must be hot enough to avoid fragmenting, but not so hot that radiation pressure prevents collapse. Heavy elements must be absent because they facilitate cooling and fragmentation. The radiation environment must be just right. Getting all these conditions simultaneously is difficult. Models suggest direct collapse should be rare. Yet if the high redshift quasars require it to explain their masses, direct collapse might be common. This would require understanding why early universe conditions favoured it. Another possibility was that black holes grew through super Eddington accretion. The Eddington limit is not a hard boundary, but a point where radiation pressure from the accretion process becomes strong enough to blow away infalling matter. Black holes can exceed this limit temporarily if gas falls in from multiple directions, or if the geometry allows radiation to escape in jets rather than spherically. Super Eddington accretion could be 2, 5, even 10 times faster than Eddington limited growth. This would shrink the timeline needed to reach billion solar mass. But sustaining super Eddington accretion for hundreds of millions of years requires continuous gas supply and specific configurations. Is it plausible that early quasars maintained such conditions for so long? Mergers offered yet another growth channel. If many black holes formed in the early universe and galaxies merged frequently, black hole mergers could rapidly build mass. Each merger doubles the mass if the holes are equal size. Multiple mergers could grow a black hole exponentially. Gravitational wave observations from LIGO have confirmed that stellar mass black holes merge in the present-day universe. Perhaps supermassive black hole mergers were common in the early universe, when galaxies were closer together and mergers more frequent. But even this requires starting with numerous intermediate mass seeds and having them find each other and merge within the short time available. Perhaps all these processes operated together. Direct collapse created large seeds. Super Eddington accretion grew them rapidly. Mergers added mass through collisions. In combination, maybe billion solar mass black holes by redshift 10 or 11 became barely plausible. But barely plausible is not the same as predicted or expected. Lambda CDM does not naturally produce such conditions. The model allows for supermassive black holes, but predicts they should form later, growing to billion solar mass scales around redshift 6 or 7, not 10 or 11. Finding them earlier pushed the timeline in ways that strained the model. The black hole problem connected to the galaxy problem. Black holes and galaxies co-evolve. If black holes are more massive earlier than predicted, their host galaxies should be too. And indeed, Webb found both massive galaxies and massive black holes at earlier epochs than expected. The two problems reinforced each other. Whatever process accelerated black hole growth probably also accelerated galaxy growth. Perhaps gas dynamics in the early universe allowed both structures to assemble faster. Perhaps feedback processes that regulate growth in the present-day universe were weaker or operated differently. Perhaps dark matter halos formed denser concentrations early, pulling in gas more rapidly and feeding both galaxies and central black holes. Or perhaps the issue was more fundamental. Perhaps our understanding of how structure forms in the early universe is incomplete. Perhaps top-down processes we have not properly modelled play larger roles than hierarchical bottom-up assembly. Perhaps the initial conditions had more variation than standard inflation predicts. Perhaps something about the physics of the first few 100 million years differs from later epochs in ways we have not captured. Webb was revealing that both galaxies and black holes were more advanced than predicted at high redshifts. Both problems pointed toward accelerated structure formation. Both suggested the early universe was more active and productive than models described. Some researchers proposed radical solutions. What if supermassive black holes formed first, before galaxies? Perhaps in the very early universe, enormous black holes formed through exotic processes we have not considered. These primordial black holes would then seed galaxy formation as gas collected in their gravitational wells. This reverses the usual picture where galaxies form first and black holes grow in their centers afterward. But if black holes came first, the co-evolution problem disappears. The mass correlations between black holes and galaxies would arise naturally because galaxies formed in the potential wells of pre-existing black holes. The challenge is explaining how such primordial black holes could form. Standard cosmology does not produce them. You need extreme density fluctuations far beyond what inflation predicts, or exotic physics in the first moments after the Big Bang, possible in principle, but speculative and without independent evidence. What was clear was that the supermassive black hole population at high redshift was more developed than lambda CDM predicted. More massive black holes, more numerous quasars, more active accretion. The universe, when it was just a few percent of its current age, already contained billion solar mass black holes, shining as luminous quasars. These were not rare flukes. Numerous examples had been found. The population statistics suggested this was normal for the early universe, not exceptional. And normal did not match predictions. Something about black hole formation and growth in the first few 100 million years operated more efficiently or through different channels than our models captured. Combined with the galaxy problem and the structure problem, the black hole observations added to the mounting evidence that Webb was revealing a universe fundamentally different from the one lambda CDM described. More mature, more structured, more active, a universe that had accomplished in a few 100 million years what should have taken billions. The timeline did not work, and fixing it would require either revising physics or revising cosmology, or both. Every cosmology textbook contains a timeline, a diagram showing how the universe evolved from the Big Bang to the present. Time runs along the horizontal axis, usually logarithmic, to compress the enormous range from fractions of a second to billions of years. The vertical axis shows various epochs and events. The Planck era, when quantum gravity dominated, inflation exponentially expanding space. The quark gluon plasma, cooling into protons and neutrons. Big Bang nucleosynthesis, forging light elements. Recombination, when atoms formed and the cosmic microwave background was emitted. The Dark Ages, when no stars yet shone. Then reionization, as the first stars ignited. Galaxy formation beginning modestly and accelerating over time. The timeline is elegant, well-defined, tested against countless observations. Students memorize it. Researchers use it as the framework for understanding cosmic evolution. It is the story of how we got here from there. Webb is forcing us to redraw that timeline. Not completely. The overall sequence remains valid. The universe did expand from a hot, dense state. Inflation did occur. The cosmic microwave background did form when the universe was 380,000 years old. These pillars of cosmology stand firm, but the later epochs, from the Dark Ages through galaxy formation, need revision. Events happened earlier, structures formed faster, the universe transitioned from simple to complex more rapidly than the textbooks describe. The timeline needs compressing, shifting events leftward toward earlier times, squeezing more evolution into less time. The Dark Ages were not as dark as we thought. This epoch, from recombination at 380,000 years until the first stars formed around 100 to 200 million years, was supposed to be a period when the universe expanded and cooled with no sources of light except the fading cosmic microwave background. Dark matter halos were collapsing. Gas was falling into them. But stars had not yet ignited. The universe was dark and simple. Webb's observations suggested this dark age was shorter than predicted. The first stars formed earlier. Galaxies began assembling sooner. Light filled the universe before we expected. The Dark Ages might have lasted only 50 to 100 million years rather than 200 or more. Ionization happened earlier too. This is the process where ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen pervading space. Before ionization, the universe was filled with neutral hydrogen atoms. Ultraviolet photons from early stars had enough energy to strip electrons off hydrogen, ionizing it. As more stars formed and more radiation filled space, the ionized regions grew and merged. Eventually, the entire universe transitioned from neutral to ionized. This is a major phase transition in cosmic history with important observational consequences. Neutral hydrogen absorbs ultraviolet light. Ionized hydrogen is transparent. The timing of ionization affects how far we can see in ultraviolet wavelengths and shapes the spectra of distant quasars. Measurements of the cosmic microwave background constrain ionization timing through its effect on photon scattering. The Planck satellite determined that ionization occurred around redshift 8 to 9, corresponding to 500 to 600 million years after the Big Bang. This timing matched models where galaxies gradually formed and their combined ultraviolet output slowly reionized space over a few 100 million years. But Webb's discovery of numerous massive galaxies at higher redshifts suggested reionization might have started earlier. If bright galaxies existed at redshift 12, they would have been producing ultraviolet radiation that contributed to reionization. Perhaps reionization began earlier and proceeded faster than models based on pre-Webb galaxy populations predicted. The peak epoch of star formation also needed revisiting. Previous observations found that cosmic star formation peaked around redshift 2, about 10 billion years ago, when the universe was roughly 3 billion years old. Before that peak, star formation was increasing as more galaxies formed and grew. After the peak, star formation declined as gas supplies depleted and galaxies aged. This seems sensible. The universe needed time to build up gas supplies in galaxies before star formation could proceed vigorously. But Webb found extremely high star formation rates at much higher redshifts. Galaxies at redshift 10 were forming stars at rates rivaling galaxies at the supposed peak epoch. Perhaps the peak was not at redshift 2, but occurred earlier. Or perhaps there was no single peak, but a long plateau of high star formation extending from very early times through to a few billion years ago. The supermassive black hole growth timeline needed complete overhaul. Previous models suggested black holes grew most rapidly around redshift 2 to 3. the same epoch when star formation peaked. This made sense because black hole accretion and star formation both require gas supplies and both occur in galaxy centers where gas is concentrated. Coordinated growth of black holes and galaxies seemed natural, but Webb found massive black holes at redshift 10 and beyond. If black holes reached billions of solar masses by 500 million years after the Big Bang, their peak growth must have occurred even earlier. Perhaps black holes formed and grew most rapidly in the very first few 100 million years, then settled into slower growth rates afterward. This reverses the previous picture. Galaxy assembly also required rethinking. The hierarchical models predicted small galaxies forming first, then merging into larger systems over billions of years. The average galaxy mass should increase with time. Large galaxies should be rare at high redshift and common at low redshift. Webb showed that large massive galaxies existed earlier than this picture allowed. Perhaps hierarchical assembly was not the whole story. Perhaps some massive galaxies formed early through processes we had not properly incorporated. Or perhaps mergers occurred faster in the early universe when everything was closer together and collision rates were higher. Redrawing the timeline meant adjusting many interconnected pieces. Change one event's timing and other events shift too because they depend on earlier conditions. If reionization happened earlier, that affected how galaxies formed afterward. If supermassive black holes grew faster early, their feedback on galaxy formation changed. If stars formed more efficiently in the early universe, the chemical enrichment history differed. Everything connected to everything else. You could not just shift galaxy formation earlier without consequences rippling through the entire timeline. Some researchers began questioning whether the Big Bang happened earlier than we thought. If the universe is older, more time is available for structure formation. But the age of the universe is tightly constrained by multiple independent measurements. The cosmic microwave background, the expansion rate, the abundances of elements, all point to 13.8 billion years. Making the universe significantly older would require revising these fundamental constraints. That seemed more drastic than revising how structure forms within the accepted age. Others suggested cosmic variance was larger than assumed. Perhaps the regions Webb observed were unusually dense, where structure formed earlier than typical regions. If we happened to point Webb at rare overdense patches, we would see anomalously early and massive structures. But Webb surveyed multiple independent fields. All showed similar populations of early massive galaxies and quasars. If these were all rare overdense regions, we were extraordinarily unlucky in our field selection. More likely, what Webb saw was representative of the universe at those epochs. What seemed inescapable was that the cosmic history narrative needed substantial revision. Not abandonment, not starting from scratch, but significant modification of the later chapters describing how galaxies and structures formed. The universe evolved faster, accomplished more earlier, reached maturity sooner than the pre-Webb timeline described. This was not just correcting details, this was recognizing that the pace of cosmic evolution was fundamentally faster than we had understood. Textbooks would need rewriting, simulations would need adjusting, models would need new parameters or new physics. The timeline drawn from decades of observations was being challenged by a single telescope's first years of data. That is how science progresses, not smoothly, not predictably, but in jumps when new capabilities reveal previously hidden truths. Webb was providing such a revelation, and the cosmic history it was revealing was one of a universe that wasted no time. That jumped immediately into vigorous structure formation. That reached impressive maturity while still in its cosmic infancy. A universe bigger, faster, more productive than we imagined when we drew timelines based on what earlier telescopes could see. The problems Webb revealed are not isolated puzzles. They're interconnected symptoms of a deeper issue. Lambda CDM, the standard cosmological model, is not merely wrong in a few details. It is systematically under-predicting cosmic structure at early times across multiple independent observations. Galaxies too massive, black holes too large, star formation too vigorous, structures too advanced, cosmic infrared background too bright. Every measurement suggests the early universe was more active than predicted. When a model fails in one area, you can adjust that specific component. When it fails across the board, the failures point to something fundamental missing from the framework. This is what researchers are calling the cosmological crisis. Not because cosmology is collapsing, not because we know nothing, but because our best model is clearly incomplete in ways we do not yet understand, and the solution is not obvious. It is a crisis of understanding, rather than a crisis of total ignorance. We have a model that works extraordinarily well in many contexts. The cosmic microwave background, the expansion history, the abundances of light elements, the large-scale structure at low redshifts, all beautifully explained by lambda CDM. But add Webb's observations of the high redshift universe and the model struggles. The success in some areas makes the failure in others more glaring. A model cannot be mostly right. Either it correctly describes nature or it needs modification, and lambda CDM clearly needs modification. What kind of modification? This is where the crisis lies. Dozens of papers have been published proposing solutions. Change star formation efficiency, modify initial conditions from inflation, add new dark matter physics, invoke modified gravity, adjust reionization models. Each proposal fixes some observations, but typically fails others, or requires fine-tuning that seems unnatural. No clear winner has emerged. No single modification to lambda CDM obviously solves all the problems without creating new ones. Researchers are exploring many directions simultaneously, hoping observations will eventually point toward the right path. But for now, uncertainty reigns. Some physicists are questioning fundamental assumptions. Is the cosmological principle correct? This is the idea that the universe is homogeneous and isotropic on large scales, looking the same everywhere and in all directions. Lambda CDM is built on this assumption. If it is wrong, if the universe has large-scale structure or variations we have not accounted for, then using a model that assumes uniformity would give incorrect predictions. Perhaps our observable universe is not representative. Perhaps we occupy an unusual region. Perhaps structure varies across larger scales than we can observe. Abandoning the cosmological principle would be radical. It would require rebuilding cosmology from scratch. But if it is necessary to explain observations, we cannot cling to assumptions just because they are convenient. Others question whether general relativity is correct on cosmological scales. Einstein's theory has passed every test in the solar system, and with binary pulsars and with gravitational wave observations. But these test strong field regimes or small scales. The largest scales and weakest fields might behave differently. Perhaps gravity has corrections that only become important when averaged over billions of light years or billions of years. Modified gravity theories have been constructed that reproduce general relativity successes while differing in cosmological contexts. Some can explain cosmic acceleration without dark energy. Others affect structure formation rates. Could modified gravity explain what Webb is seeing? The challenge is that modifying gravity is difficult. General relativity is elegant and constrained. Changing it without breaking what works is hard. The detection of gravitational waves from neutron star mergers in 2017 provided stringent constraints. Gravitational waves must travel at the speed of light to within 1 part in 10 to the 15th. This rules out many modified gravity theories that predict different propagation speeds. The remaining viable theories are limited and must be carefully constructed to satisfy all observational constraints while still differing enough from general relativity to explain Webb's observations. Perhaps dark matter is more complex. Lambda CDM treats dark matter as cold, meaning the particles move slowly, and collisionless, meaning they only interact gravitationally. But we do not actually know what dark matter is. Decades of direct detection experiments have found nothing. Perhaps dark matter has properties we have not anticipated. Perhaps it self-interacts, with particles scattering off each other. Perhaps it comes in multiple species with different masses. Perhaps it interacts weakly with normal matter through forces we have not detected. Any of these could affect structure formation. Self-interacting dark matter can create denser halos that form earlier. Multiple dark matter species might have different clustering properties. Dark matter interactions with normal matter could affect gas dynamics and star formation. Exploring these possibilities requires building new models and testing them against observations beyond just Webb's high redshift data. Dark energy might also be more complex than a cosmological constant. If dark energy density evolved over time, this would affect cosmic expansion, history, and structure growth rates. Perhaps dark energy was weaker in the early universe, allowing more rapid structure formation before it came to dominate. Or perhaps dark energy interacts with dark matter or normal matter, coupling the components in ways that affect their evolution. Dozens of dynamical dark energy models exist. Most are constrained by observations showing that dark energy behaves very much like a constant, but perhaps subtle evolution exists within current measurement uncertainties that could be relevant for explaining early structure formation. The crisis is also one of theoretical framework. Lambda CDM is based on the Friedmann equations, which describe a homogeneous isotropic universe. This is a tremendous simplification. The real universe has structure. Galaxies, clusters, voids. The Friedmann equations average over all this, treating the universe as smooth on average. But what if the averaging breaks down? What if back reaction from structure affects global expansion in ways the simple equations do not capture? Some researchers argue that structure formation itself generates effects that mimic dark energy or modify expansion rates. If true, the need for dark energy might be reduced and cosmic evolution might proceed differently than Lambda CDM predicts. This is controversial. Most cosmologists think back reaction is too small to matter, but it remains a possibility worth exploring. Perhaps the solution requires multiple modifications simultaneously, not just changing one component, but adjusting several. Modified dark matter plus modified dark energy plus better star formation models. Any single change might be insufficient. Combined, they might explain observations, but adding multiple modifications increases complexity and reduces predictive power. A model with many adjustable parameters can fit any data but explains nothing. The goal is to find the minimal set of changes that fix the problems without making the model unwieldy. This is an art as much as science, judgment about what modifications are reasonable and what are contrived. What has independent motivation versus what is added solely to fit problematic data. The cosmological crisis is uncomfortable. For decades, Lambda CDM reigned as the standard model. Researchers built careers on it. Textbooks were written. The model seemed so successful that the impression emerged that cosmology was nearly complete. We knew the age of the universe, its composition, its history. Just details remained to be filled in. Webb has shattered that complacency. The details matter. They are not fitting the model, and when pressed, the model is not explaining them. This is not disaster. This is opportunity. The most exciting moments in science come when established frameworks fail and new understanding emerges. We are living through such a moment. Webb has opened a window into the early universe that reveals it to be different from predictions. The crisis lies in figuring out what that difference means, what it tells us about physics or cosmology or our place in the cosmos. The answer will reshape our understanding. It will lead to new models, new predictions, new tests. Science thrives on such challenges, and the cosmological crisis, uncomfortable as it is for those invested in Lambda CDM, is pushing the field forward in ways that will ultimately deepen our knowledge of the universe, its history, and its future. Looking back with the benefit of Webb's observations, where did we go wrong? How did our models fail to predict what was actually out there? This is not just academic exercise. Understanding our mistakes helps avoid repeating them and points toward what needs fixing. Several areas stand out where assumptions or simplifications led Lambda CDM astray, and examining them reveals how difficult cosmology is when we can only observe a tiny fraction of cosmic history with instruments that have limited reach. First, star formation. Lambda CDM includes prescriptions for how gas turns into stars, based on observations of nearby galaxies and theoretical understanding of gas physics. These prescriptions work well for present-day galaxies, but extrapolating them to the early universe assumed continuity. We assumed star formation operated the same way at high redshift as it does now. Webb shows this was wrong. Early galaxies formed stars more efficiently, perhaps because the gas was less enriched with heavy elements, allowing different cooling mechanisms. Perhaps because gas densities were higher in the young compact galaxies. Perhaps because feedback processes were less effective at regulating star formation. Whatever the reason, the star formation efficiency we use in models was too low for the early universe. This mistake propagated through all predictions, causing us to underestimate how many stars formed and how quickly galaxies grew. Second, black hole seeding. We assumed supermassive black holes grew from stellar mass seeds, a 100 solar mass black hole left behind when a massive star explodes. This seed accretes matter over hundreds of millions of years to reach billion solar mass scales. But Webb found billion solar mass black holes too early for this growth channel alone. We were wrong about the seeds. Either they were much more massive than stellar remnants, forming through direct collapse mechanisms we had not properly modelled, or black holes grew through super Eddington accretion that we thought should be rare but was actually common, or black hole mergers were more efficient at building mass than we realised. Likely some combination of all three, but the bottom line is that our black hole formation models were incomplete. We missed physics that was important in the early universe. Third, merger rates. Lambda CDM predicts how often dark matter halos merge. Small halos form and grow by merging with each other. Galaxies in those halos merge too. We calculated merger rates based on simulation and used them to predict how galaxies should grow. But perhaps mergers happened faster in the early universe than models suggested. Everything was closer together. Velocities were different. Perhaps the merger process was more efficient at early times. If so, galaxies could assemble faster through accretion of smaller systems. This would help explain why massive galaxies appeared earlier than hierarchical models predicted. We may have underestimated how quickly the merger process could build structure. Fourth, feedback. When stars form and explode as supernovae, they release energy that heats surrounding gas. This feedback can blow gas out of galaxies, suppressing further star formation. Similar feedback comes from accreting supermassive black holes. The radiation and winds from active galactic nuclei can heat or expel gas. These feedback processes regulate galaxy growth in the present-day universe. We included them in models and assumed they operated the same way in the early universe. But maybe they did not. Maybe feedback was weaker early on. Maybe the gas dynamics were different. Maybe black hole feedback had not yet become important because supermassive black holes were still growing. Weakening feedback would allow galaxies to grow faster and larger. We may have overestimated feedback's regulatory role at high redshifts. Fifth, initial conditions. Lambda CDM uses initial conditions from the cosmic microwave background. The tiny fluctuations observed at recombination seed, all later structure. We assume these fluctuations are Gaussian random with a specific power spectrum. This assumption is testable and has been tested. The cosmic microwave background matches Gaussian predictions well, but well is not perfectly. Small deviations might exist. Non-Gaussian components or small changes to the power spectrum on certain scales could affect structure formation without dramatically altering the cosmic microwave background appearance. Perhaps the initial conditions were slightly different than our simplest inflation models predict in ways that favoured earlier structure formation. We might have oversimplified the initial conditions by assuming perfect Gaussianity. Sixth, cosmic variance. The universe is not perfectly uniform. Some regions are denser, some less dense. Over large enough volumes, these variations average out, and the universe appears homogeneous. But on smaller scales, substantial variation exists. When we observe high redshift galaxies, we are looking at specific regions that might not be representative of the cosmic average. Perhaps Webb happened to observe unusually dense regions where structure formed earlier. If so, extrapolating from these observations to general statements about the universe might be misleading. We may have underestimated how much cosmic variance affects what we see at high redshift, though this seems less likely as more observations have been made and similar results appear in multiple independent fields. Seventh, dust and obscuration. Dust grains in galaxies absorb ultraviolet and visible light and re-emit it in infrared wavelengths. This obscures our view of stars and can make galaxies appear fainter than they are. In the early universe, dust properties might differ from today. Perhaps less dust formed because supernovae had not yet enriched the interstellar medium with enough heavy elements. Or perhaps dust was more abundant or clumped differently. If our dust corrections were wrong, we could have underestimated the luminosities and masses of high redshift galaxies. Webb's infrared vision penetrates dust better than optical telescopes. That is part of why it sees more, but it also means comparing Webb's observations to earlier optical observations requires careful accounting for dust differences. We may have gotten this wrong. Eighth, the measurement techniques themselves. Determining galaxy properties from their light requires modelling. We observe brightness in different wavelength bands. We fit this photometry against models of stellar populations to infer mass, age, star formation rate. The models make assumptions about what kinds of stars exist and how their light combines. If early galaxies had different stellar populations than we assumed, say more massive stars or different age distributions, our mass estimates could be systematically wrong. Perhaps the galaxies are not as massive as initial estimates suggest, or perhaps they are even more massive. Better spectroscopy will refine these estimates, but our initial methods may have been calibrated on present-day galaxies and extrapolated inappropriately to the early universe. None of these mistakes is embarrassing. Cosmology is hard. We are observing objects billions of light-years away using physics we cannot test in laboratories. Extrapolating from present-day observations to the early universe requires assumptions that may not hold. Models must simplify enormously complex physics to be computationally tractable. We do the best we can with available data and understanding. When new data arrives and shows our models were incomplete, that is progress, not failure. It means we are learning. Webb is teaching us where our assumptions broke down, where our simplifications were too simple, where our physics was incomplete. This is invaluable. It points directly at what needs fixing. The next generation of models will incorporate what we have learned from Webb. They will include more sophisticated star formation physics, calibrated on high redshift observations. They will implement better black hole seeding mechanisms. They will adjust merger rates and feedback based on what Webb shows actually happened. These improved models will make better predictions. And when even better telescopes observe even further into cosmic history, we will undoubtedly find new surprises that our improved models miss. That is the nature of science. We build models that explain current observations. We use those models to predict what future observations will reveal. When predictions fail, we learn and improve. Webb showed us what we got wrong. Now the work begins to get it right. Webb is just the beginning. As revolutionary as its observations have been, it has limitations. Its mirror is 6.5 meters across, large for a space telescope, but small compared to the largest ground-based observatories. Its field of view is tiny, surveying small patches of sky. Its lifetime is limited, perhaps 20 years, if all goes well with fuel reserves and instrument health. What it has revealed in its first years will be built upon by future observatories, even more powerful, observing deeper, wider, with capabilities Webb cannot match. These next-generation telescopes are being designed and built now, and they will push into cosmic territory that even Webb cannot access, testing cosmological models in ways that should finally resolve whether lambda CDM needs minor tweaking or major overhaul. The Nancy Grace Roman Space Telescope will launch in the mid-2020s. Roman's mirror is slightly smaller than Webb's, but its camera covers a field of view 100 times larger. This makes Roman a survey machine. Where Webb peers deeply into small regions, Roman will map huge swathes of sky, detecting billions of galaxies. Its infrared sensors will find high redshift galaxies in enormous numbers, providing statistics that Webb's small fields cannot. Roman will determine whether the massive early galaxies Webb found are common or rare. If they are common, the problem is worse for lambda CDM. If they are rare statistical flukes, the tension eases. Roman will answer this within its first few years of operation by surveying volumes hundreds of times larger than Webb can observe in reasonable time. The ground-based extremely large telescope is under construction in Chile. Its mirror will span 39 meters, nearly 6 times Webb's diameter. Larger mirrors collect more light, allowing fainter objects to be detected. The ELT will see galaxies Webb cannot and will obtain detailed spectra that characterize their properties precisely. Understanding the stellar populations, chemical compositions, and dynamics of high redshift galaxies requires spectroscopy. Photometry can estimate these properties, but with large uncertainties. Spectroscopy measures them directly. The ELT will take Webb's discoveries and study them in detail, determining exactly how massive the galaxies are, how fast they are forming stars, what their structures look like. This will test whether they truly are as anomalous as they appear or whether better measurements bring them into consistency with predictions. The Giant Magellan Telescope, another ground-based behemoth with a 25-meter effective aperture, will also contribute. Multiple such large telescopes are needed because telescope time is precious and observations are slow. High redshift galaxies are faint. Obtaining good spectra takes hours even with the largest mirrors. Hundreds of galaxies need to be studied to build statistical samples. No single telescope can do this alone in reasonable time. The community is building multiple large observatories that will work in parallel, each contributing to the effort. The square-kilometre array, when completed, will revolutionize radio astronomy. Its square kilometre of total collecting area dwarfs any existing radio telescope. SKA will detect neutral hydrogen emission from galaxies across cosmic history, including the epoch Webb is observing. Hydrogen maps trace where gas is located and how it moves. This is crucial for understanding galaxy formation, because stars form from gas. Webb sees the stars already formed. SKA will see the gas reservoirs feeding star formation. Combining Webb and SKA observations will give a complete picture of how galaxies were assembling in the early universe, how much gas they contained, how efficiently they converted gas to stars, where the gas came from and where it went afterward. Gravitational wave observatories are advancing too. The Laser Interferometer Space Antenna, planned for the 30s, will detect low-frequency gravitational waves from merging supermassive black holes. These mergers occur when galaxies collide. By observing black hole mergers across cosmic history, LISA will trace how supermassive black holes grew. It will determine merger rates at different epochs. It will measure black hole masses independently of electromagnetic observations. This provides a completely different window into the black hole problem Webb has revealed. If LISA finds frequent mergers of massive black holes at high redshifts, this would support the idea that mergers were a major growth channel, explaining how black holes reached billion solar mass scales so early. Future cosmic microwave background experiments will also contribute. CMBS-4 will measure the microwave background with exquisite precision, constraining the early universe conditions that seeded structure formation. If initial conditions differed from the simplest predictions, CMBS-4 will detect it. If ionization happened earlier, as Webb suggests, CMBS-4 will measure this through its effect on photon scattering. The cosmic microwave background is a snapshot of the universe at recombination. Everything that happened afterward is imprinted on that snapshot through subtle effects. Measuring those effects precisely provides independent constraints on cosmic history that complement direct observations of high redshift galaxies. Computational cosmology will keep pace with observations. Simulations are already being run that attempt to match Webb's observations by adjusting physics. As faster computers and better algorithms become available, simulations will reach higher resolution and incorporate more complex physics. Eventually, simulations should reproduce what Webb sees. When they do, we will understand what combination of physics produces early massive galaxies. We will know whether lambda CDM can be adjusted to work, or whether more fundamental changes are needed. Simulations are laboratories for testing ideas. Observers provide data, theorists propose explanations. Simulators implement those explanations in computer code and see if they reproduce observations. The interplay between these approaches drives progress. Artificial intelligence and machine learning are also being applied. The data volumes from upcoming surveys are enormous. Billions of galaxies, each with photometry in multiple bands and sometimes spectra. Extracting information requires sophisticated analysis. Machine learning algorithms can identify patterns humans miss. They can classify galaxies, estimate properties, detect anomalies. AI is already being used to find high redshift galaxy candidates in Webb data. As techniques improve, machine learning will become an essential tool for making sense of the flood of data from next-generation observatories. The combination of better telescopes and better analysis methods will accelerate discovery. Within the next decade, the observational landscape will be completely transformed. Webb will have completed deep surveys over significant areas of sky. Roman will have mapped enormous volumes. The ELT and GMT will have obtained detailed spectra of thousands of high redshift galaxies. SKA will have traced neutral hydrogen across cosmic history. LISA preparations will be advancing. CMBS-4 will be taking data. The accumulation of observations will either vindicate lambda CDM by showing that the early anomalies were misinterpretations or measurement errors, or will conclusively demonstrate that the model is incomplete. Either way, we will know far more than we do now. The cosmological crisis will be resolved, not necessarily with all answers. Science always leaves questions for the next generation, but the specific tensions Webb has revealed will be understood. We will know whether they point to new physics or to better understanding of known physics. The universe Webb revealed, bigger and more active than we imagined, will be mapped in detail, and whatever we learn will set the stage for the next set of questions, the next generation of telescopes, the next era of cosmic discovery. There is a possibility that almost no one wants to seriously consider, a possibility that seems too far-fetched, too untestable, too much like science fiction to be taken seriously. But it keeps appearing in discussions among theorists trying to explain Webb's observations. What if the universe is bigger than we think, not just in the sense of containing more galaxies than we counted, but fundamentally bigger in the sense of being part of a much larger structure? What if our observable universe is one region within a vastly larger cosmos that has properties we have not accounted for? What if the multiverse is real? The multiverse idea comes from inflation theory. Standard inflation posits that space underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. This solves several cosmological puzzles and makes predictions that match observations beautifully. But inflation theory suggests something more. Once inflation starts, it may not stop everywhere simultaneously. Quantum fluctuations could cause inflation to end in some regions while continuing in others. The regions where inflation ends become bubble universes like ours. The regions where inflation continues keep expanding exponentially and spawn more bubbles. This process, called eternal inflation, never ends globally. It produces infinite bubble universes with potentially different properties. Each bubble could have different vacuum states, different physical constants, different particles and forces. Most physicists accept inflation occurred. The evidence from the cosmic microwave background is compelling. But eternal inflation and the multiverse it implies are more speculative. We cannot observe other bubble universes. They are beyond our cosmic horizon, separated by exponentially expanding space. No signal can reach us from them. No observation can confirm they exist. The multiverse is a prediction of inflation theory, but an untestable one. This makes many scientists uncomfortable. Predictions should be testable. If they are not, are we doing science or philosophy? Yet the multiverse might be relevant for understanding Webb's observations. If our universe is one bubble among many, interactions between bubbles during early cosmic history could have effects. Suppose two bubble universes formed close together during inflation. Before eternal expansion separated them, they might have collided. The collision would release energy, affecting both bubbles. From inside one bubble, we might observe signatures of such a collision. Asymmetries in the cosmic microwave background, unusual large-scale flows of matter, regions where structure formed differently than elsewhere. Some of the anomalies Webb and other telescopes have found might be explained as collision effects. More speculatively, if bubble universes are close in some higher dimensional space, they might interact gravitationally across the extra dimensions. This could affect how matter clumps and how structures form. Perhaps the early rapid structure formation Webb observed was enhanced by gravitational influence from nearby bubble universes. Matter in our universe feeling gravity from matter in adjacent universes, pulling harder than we account for in models that assume our universe is isolated. This would accelerate structure formation in ways that look like more efficient star formation or faster black hole growth, but are actually extra-dimensional gravitational effects. These ideas are highly speculative. No concrete evidence supports them, but they are being discussed because more conventional explanations have struggled. When every attempt to modify lambda CDM within its standard framework fails to explain observations, researchers start considering more exotic possibilities. The multiverse at least has the virtue of being predicted by inflation, which we believe occurred. It is not invented solely to explain Webb's data. It is a theoretical possibility that might happen to be relevant. Testing multiverse ideas is extraordinarily difficult. We cannot observe other universes directly, but we can look for their effects. Bubble collisions should leave specific signatures. Circular patterns in the cosmic microwave background with particular temperature profiles. Preferred directions in large-scale structure. Asymmetries that correlate with the collision direction. Searches for such signatures have been conducted. Some claim marginal detections, others find nothing. The statistical significance is weak. Nothing definitive has emerged, but the searches continue with better data. Gravitational effects from other universes would manifest differently, perhaps as an anomalous component to cosmic expansion that mimics dark energy but has different properties. Perhaps as modifications to structure formation rates that vary across our universe depending on where nearby bubbles are positioned in extra dimensions. Detecting such effects requires extremely precise measurements of expansion history and structure growth across different regions of our observable universe. Future surveys might provide the needed precision. The multiverse is also invoked to explain fine-tuning. Why are the constants of nature in our universe so precisely calibrated to allow complex structures and life? In a multiverse, every possible set of constants exists in some bubble. We necessarily find ourselves in a bubble with life-permitting constants because we could not exist elsewhere. This anthropic explanation for fine-tuning is controversial, but at least makes sense if the multiverse is real. Without the multiverse, fine-tuning seems like an uncomfortable coincidence demanding explanation. Could the multiverse explain why Webb finds more structure than predicted? Perhaps, if initial conditions in our bubble were affected by collisions or extra-dimensional interactions, they might have been different than standard inflation predicts. More structure on certain scales, more extreme fluctuations. This could seed enhanced structure formation without changing the physics of how structure grows. The problem would be pushed back to initial conditions rather than requiring new physics afterward. Whether this helps or just shifts the problem is debatable. Most physicists remain skeptical of using the multiverse to explain observations. The multiverse is untestable in the usual sense. We cannot go to another universe and compare its properties to ours. We cannot set up experiments that confirm or rule out the multiverse. If we invoke it to explain every anomaly, we risk abandoning the scientific principle that theories should make predictions testable by observation. A theory that can explain anything explains nothing. The multiverse might be real, but using it to solve specific observational problems is dangerous unless we have independent evidence for it beyond just needing it to fix our models. Yet the possibility cannot be entirely dismissed. Inflation is our best theory of the early universe. It makes predictions about the multiverse. If inflation is correct, the multiverse likely exists. If the multiverse exists, it might have observable consequences. Ignoring this because it makes us uncomfortable would be unscientific. The question is whether any effects are actually detectable, or whether the multiverse remains forever in the realm of speculation. Webb has not provided smoking gun evidence for the multiverse, but it has revealed a universe that defies explanation within our simplest models. If conventional physics cannot explain what Webb sees, perhaps we need to think bigger. Perhaps the universe really is bigger than we thought. Not just more galaxies, but more realities. An infinite collection of bubble universes, each with its own history, evolving in a vast inflating space that dwarfs even the observable cosmos we can see. It sounds like fantasy, but quantum mechanics and general relativity, our two most successful theories, both describe realities stranger than everyday experience suggests. Perhaps the multiverse is real, and perhaps Webb is giving us our first glimpses of its effects. Webb has been operational for less than 3 years. In that time, it has upended cosmology. Not destroyed it, not shown that everything we believed was wrong, but revealed that our models, successful as they are incomplete in significant ways. The universe Webb is showing us is bigger than we imagined, not just more galaxies, though there are more, not just brighter, though it is, bigger in the sense of more complex, more active, more mature at earlier times than our theories predicted. Bigger in the sense that what we thought was settled science turns out to have surprises lurking in the data. Bigger because every time we think we understand it, the universe reveals new layers that challenge our understanding. This is not new. The history of astronomy is a history of discovering the universe is bigger than we thought. For most of human history, the universe was the earth and heavens above. Then Copernicus showed Earth orbits the sun. The universe became the solar system. Then telescopes revealed other stars like our sun. The universe became the Milky Way galaxy. Then Hubble showed other galaxies existed beyond ours. The universe became billions of galaxies scattered across space. Then Hubble showed the universe was expanding, that it had a beginning, that it evolved from a hot, dense state. The universe became dynamic, with history and future. Each discovery expanded our conception of how large and complex reality is. Webb is the latest chapter in this story. It is showing that the universe 13 billion years ago was not the simple place we thought, not a pristine darkness with just the first faint glimmers of structure, but already rich with galaxies, black holes, complex processes, already resembling the mature universe we observe around us in many ways. The timeline of cosmic evolution is compressed. Things happened faster. The universe got interesting sooner. This is a revision, on par with earlier discoveries that expanded our cosmic horizons. And like earlier discoveries, it will take time for the full implications to be understood. What will we learn in the next decade as Webb continues observing and new telescopes join it? We will determine whether the early massive galaxies are common or rare. We will measure black hole masses precisely across cosmic history. We will trace when reionization occurred and what sources contributed. We will map how structure grew from the Dark Ages through to the present day. We will test whether lambda CDM can be adjusted to explain observations or whether new physics is needed. These are not abstract questions. These are concrete measurements that will resolve current uncertainties. We will also likely find new surprises. Webb is still exploring. Every deep field reveals unexpected objects, galaxies with strange properties, quasars where they should not be, structures that challenge expectations. The list of anomalies will probably grow before it shrinks. That is how discovery works. New capabilities reveal new phenomena. Our models must catch up. The process is iterative. Observe, model, test, revise. Each cycle deepens understanding. We are in the observation phase now, accumulating data faster than theories can assimilate it. The modeling and testing phase will follow as researchers figure out what the data means. The ultimate lesson from Webb might be humility. We thought we had cosmology largely figured out. Lambda CDM explained so much. The cosmic microwave background, the expansion history, structure formation, it seemed like we were filling in details rather than discovering new fundamentals. Webb has shown this was hubris. The details matter. They do not fit the model. And they are telling us something important about physics, or cosmology, or both. We do not yet know what, but we are learning to listen. Learning that the universe is always more than our models capture, always bigger, stranger, more full of surprises than we imagine. Perhaps this should not surprise us. We are small creatures, on a small planet, orbiting an ordinary star in an ordinary galaxy. Our observations extend back just decades or centuries, depending on how you count. The universe is billions of years old and incomprehensibly vast. Why should our first comprehensive models be correct? Why should nature conform to our expectations? The universe does not care what we think it should be. It simply is what it is. Our job is to observe it carefully, model it honestly, admit when our models fail, and learn from failures. Webb is teaching us where we went wrong. That is invaluable. Better to discover your model is incomplete than to remain ignorant of its failures. The universe Webb is revealing will keep astronomers busy for decades. More massive galaxies will be found. More quasars, more structures. Each will refine our understanding. Eventually patterns will emerge. The pieces will fit together. We will understand why the early universe was more active than predicted. We will know whether dark matter is more complex, whether dark energy evolves, whether gravity needs modification, whether the multiverse is real. These questions that seem intractable now will have answers. Not complete answers, science never finishes, but better answers than we have today. Answers grounded in observation rather than assumption. Answers that pass quantitative tests rather than just qualitative agreement. This is progress, and when we have those answers, when the current crisis is resolved and new models explain Webb's observations, we will build even better telescopes. Telescopes that observe even deeper, even further back in time, even more precisely. And those telescopes will undoubtedly find new surprises, new anomalies that our improved models do not predict, new phenomena that challenge our updated understanding. The cycle will continue. This is not frustrating. This is what makes science exciting. The universe is an infinite frontier. We will never reach the end. There will always be more to discover, more to understand, more to be surprised by. Webb has shown us that the frontier is closer than we thought, that we do not need to look beyond the observable universe to find mysteries. They are right here, in our cosmic backyard, in the first billion years after the Big Bang, in the processes that formed galaxies and black holes, in the structure of cosmic history. The universe we can see with our best telescopes is already full of surprises, already bigger than we imagined, and we have only just begun to explore it properly. The next decade will be extraordinary. The universe is waiting to show us just how much bigger it really is. The universe revealed by the James Webb Space Telescope is not the universe we expected. It is bigger, earlier, more complex, more active, more full of galaxies, black holes, structure than our models predicted. This is not disaster. This is opportunity. The universe is teaching us where our understanding is incomplete. It is showing us where new physics might hide. It is reminding us that reality is always richer than our theories capture. And it is inviting us to expand our thinking, to question our assumptions, to imagine bigger. The cosmos has always been more than we thought. Webb has simply shown us how much more. And that is just the beginning.